Hey, what's up? My name is Victor, and today I'm going to explain you how to fit a first-order model with delay to the step response of a system. First, let's talk about a first-order model that is a mathematical representation of how a process or a real system behaves over the time when a stimulus is applied to its inputs. Uh, Also, there are three different types of a first-order model. Uh, One of them is with a zero-free, another one is with a zero, and the last one is with a non-zero zero. The main characteristic of a first order model are that they have a single pole and that they are represented by an ordinary first order differential equation. And also, an example of a first order model can be an RC circuit in where the capacitor is the component in charge of storing the energy of a system. Then let's talk about a first order model with delay, and let's explain its transfer function. We have the capital H or the capital Y, that means the system output, over the alpha or capital U, that means the system input, and that is equal to the capital K, that means the gain of the system, over the tau or capital T, that means the time constant, and at this point we add the delay term, that is a theta or a tau. And unstable time delayed processors are frequently encountered in chemical and industrial process. Also, the time delays are due to various circumstances, such as material transport, the effect of recycling loops, and even in the approach of higher order system to low order systems. And there are two simple solutions uh, for a first order model with delay. The first one is to ignore the delay term and design a controller for the delay-free process and apply the design control to the delay process. It is clear that this method only works in the case of processes that have a sufficiently small delay. And the second solution is to not ignore the delay term. Well, here we can see an step response and also the response of a system. These are two examples of a first order model with and without delay. And we can see in this example that nothing happens until tau. This is the one that has a first order model with delay. And this is the example of a first order model without delay. Here we have our first exercise. Here we can see the step response. Here we can see the system response. But this exercise, we are going to solve it ignoring the delay term. Here you can see the tau. Well, when you ignore the delay term, firstly, you need to find the settling time of the system response. Uh, for this example, the settling time was at 2 seconds, and the expression says that 4 times the time constant is equal to the settling time. So here we have our value. Then we need to apply the final value theorem in order to find the gain of the system. Here we have how to apply it, and finally we get that the gain of the system is equal to the final value of the system's response equal to the gain of the system times the final value of the step response, or the value of the step response. And finally we get our gain of the system. Then we just substitute into the uh, first order model, and we get our transfer function. And then here we have an example. This is an RC circuit, and this is the solution of the differential equation of this example. We are not going to get into details of how we get this solution of the differential equation, but if you want to know how we reach this solution of the differential equation, you can just find the process into the references. And for this example, we have that the time constant is equal to the resistor times the capacitor, and that is equal to 0.5. That was calculated just here. Then we have the same example, but in this time we are not going to ignore the delay. So when you calculate the step response with the system, you obtain this expression of the response. And we are going to use this expression to find the parameters of the system response. Those are time points, and when you substitute those time points in the expression, uh, we have that when the time is equal to this time point, the response reach point 283 percent of the final value, and when the time is equal to this time point, we have that the time that the response reach point 632 percent of the final value. Then those are the parameters that we found with the time points. So then we just observe what are the values of the x-axis, that the x-axis is the time, and then we just have that those values of the x-axis are equal to the time points that we have before. And then at this moment we have two knowns and two equations, so we just solve them and we obtain the values of the time constant and the delay. Uh, then we obtain the gain of the system applying the final value theorem. The procedure is the same as before, so the value is going to be the same as if we ignore the delay, and then we just substitute the values we have on the transfer function with delay. So we have our parameters, the gain of the system, the time constant, and the delay. And finally, for our example, that is RC circuit, we have that the value is this one. And as I told you before, you can find on the references how we reach to this expression. Finally, I want to tell you thanks for watching. I hope you understood the importance of taking into account the delay on a system response, because as you see, the values when you take into account the delay and when you ignore it are different. So sometimes the delay seems to be very small, and it seems to be easier just to ignore it and solve the problem. But even with the delay is small, it affects the results you obtain. So that's all, and as I told you before, thanks for watching.